Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be looking at Paper 1 topical questions on the topic of deformation of solids for Cambridge A-Level Physics, CAIE A-Level Physics 9702. Now, these questions are from the Papa Cambridge topical past paper questions for Paper 1, and I'll leave a link in the description of this video so that you can find these questions. There are many questions from all of the topics on AS Physics for Paper 1 and even Paper 2, and we will just be focusing on questions 638 through question 647 in this video, but there's enough there that you can use to practice if you're practicing topic by topic. So deformations of solids, this is a topic that is not that long, but it can get quite complex, as we'll see in some of the problems that we're going to solve in this video. So the first question is number 638. It comes from the March 2020 exam, question paper 1, variant 2, and it's question 19 from that paper. And we start off straight away with quite a complex one. We're shown a composite rod made by attaching a glass reinforced plastic rod and a nylon rod end to end. The rods have the same cross-sectional area, and each rod is 1 meter in length. The Young modulus EP of the plastic is 40 gigapascals, and the Young modulus En of the nylon is 2 gigapascals. The composite rod will break when its total extension reaches 3 millimeters. And we want to know what the greatest tensile stress that can be applied to the composite rod is before it breaks. So this is quite complex because we want to know the total extension of the rod, but the rod is made from two halves, one half being plastic and the other half being nylon. Now, how do we start this? We're given lots of information. Well, essentially, we want an equation that will give us the total extension, because the extension of the nylon plus the extension of the plastic will give us the total extension, and then we can use that equation to eventually solve for the tensile stress. So we have to figure out what we can do. So what I'm going to do is write an expression for the Young modulus, and let's just say for plastic, EP. This is the stress that the plastic undergoes, sigma p, divided by the strain for plastic, epsilon p, which means that the stress for plastic, sigma p, is equal to EP times epsilon p. And what I'm going to do now is I'm going to write the strain, epsilon p, as the extension over the original length. So this is the Young modulus for plastic times the extension for plastic, which we don't know how much of the 3 millimeters the extension for plastic is going to contribute, divided by the original length, which we simply call L0, because it is the same for both. Halves of the rod are 1 meter in original length. And so what this means is that the extension for plastic can be written as the stress that plastic undergoes times the original length divided by the Young modulus for plastic. And if I do the same thing for sigma n, the stress for the nylon, then I end up with the same thing. Sigma n is the Young modulus for nylon times the strain for nylon, which is the Young modulus for nylon times the extension of nylon divided by the original length of the nylon end of the rod. A lot of mathematics here. But I can then write an expression for the extension of nylon. It's equal to the stress felt by the nylon end of the rod times the original length L0 divided by Young's modulus for nylon, En. Notice I'm using little n for extension and big N for Young modulus, as is the notation, convention for the notation. Now the total extension of the entire rod is going to be different for each half of the rod, is the extension of plastic plus the amount that the nylon end is going to extend. And this is equal to sigma, and I've dropped the subscript n and p. Why is that so? Because the stress that's going to be felt on the nylon end is the same stress that's going to be felt on the plastic end. The force per unit area is not changing for this rod. So it's just going to be one value for sigma, and that's the value that we want to calculate, the greatest tensile stress, sigma. And this sigma will be into the original length L0 over EP plus the original length for nylon L0 as well over En, because both of them have the same original length. But guess what? I can now rearrange this equation and I can solve for the stress. So sigma is equal to the total extension. Remember, I don't know what the individual extensions are going to be, but I know what the total extension is, divided by L0 over EP plus L0 over En. Now, all of these values are known. So the total extension is 3 millimeters. That's 3 times 10 to the minus 3 meters divided by, now the original length for the plastic end is 1 meter, divided by the Young modulus for plastic, which is 40 gigapascals. That's 40 times 10 to the power 9, plus 1 meter for the nylon end of the rod, divided by its Young modulus, which is 2 times 10 to the power 9, 2 gigapascals. And in SI units, I get the tensile stress, the maximum tensile stress that will give us an extension of 3 millimeters to be 5.7 times 10 to the power 6 pascals. And this corresponds with option B. So that was quite a tricky question. You probably wouldn't need to do as many steps as I have done, but mathematically, this is how you would solve the problem. You'd have to find an expression for the total extension and then realize that sigma is the same for both ends of the rod. Realize that the original length of both ends of the rod, both rods are the same, or both materials are the same, but we don't know the individual extensions. So there's a lot of assumptions that you need to make in order to get to the final answer. So this was probably one of the more harder questions in this exam, but expect something similar to this, especially on the topic of deformation of solids, where, it's a common thing for the questions to seem a little bit on the tough side. So that was the correct answer there was B. The next question is 639. It comes from the summer 2020 exam. That's May-June 2020. It's question paper 1, variant 1, and it's question 16 from that paper. We're told that a mass attached to the lower end of a spring bounces up and down, and we are asked at which points in the path of the mass to the gravitational potential energy, the elastic potential energy, and the kinetic energy of the spring have the highest values. So you don't really need to know the topic of oscillations to do this, although it may help. But let's draw a little diagram of what's happening. So here's my mass, and this mass is bouncing up and down on the spring, and it's at its bottom point, so the spring is being extended past its equilibrium length, meaning there's some tension in the spring rather. And I'll then draw the mass bounces up from its lowest point and then moves to the equilibrium position. And at this equilibrium position, it's moving with very high speed, the highest speed that it can have when there's no extension of the spring. And then the mass moves to its highest position when the spring is compressed maximally, meaning it cannot be stretched, it cannot be compressed anymore rather. And what we can see here is that initially, my first position, I have the maximum extension. What this means is at this point, I have the highest elastic potential energy, because that's the most that the spring will extend in this motion. The spring then bounces, or the mass then bounces upward, and when it passes through the central position, the central point of its oscillation, its motion back and forth, there's no extension, and it has the highest speed. If it has the highest speed through this position, because as it's going up, it'll then slow down and stop at the highest point, and then speed downward and slow down and stop at the bottom point, then the central point has the maximum speed. And if it has the maximum speed, it must have the highest kinetic energy through the middle of the motion. So this will be bottom, middle, and top. We'll just label it so that we can answer the question easier. And at the top of the motion, it comes to rest momentarily. It's at a maximum compression, not extension in this case. So it's the spring is maximally compressed. What do we know? When the spring is maximally compressed, it will have its highest elastic potential energy, but also it's at its highest point in the motion, so it's going to have the most gravitational potential energy, because gravitational potential energy requires a datum, and we can choose the datum to be at the lowest point. So relative to the lowest point, the gravitational potential energy will be the highest. And also, since the spring is maximally compressed, its elastic potential energy will be at a maximum as well. Okay, and we're assuming that it's simple harmonic motion, which if you haven't already done A-level physics is something you'll come to later on. But what we do see is that at the top, we have the highest gravitational potential energy, which means we can already eliminate options A and B and stick to options C and D. At the middle, I have the highest kinetic energy, so that only leaves me with option C. And yes, at the bottom, I have the highest elastic potential energy, so I'm left with an option that is option C. And so that's how we go about solving a problem like this if we haven't already studied oscillations, because it is in A-level physics in the year 2 portion, the second year portion of A-level physics. But you can still sort of work this out with just simple sort of logic. So not as complicated as the initial question, but still required us to think a bit about the energy transformations happening for an object moving back and forth. Now 640 says, again, this is from summer 2020, question paper 1, variant 1, it's question 20 from that paper. It says a tensile force is used to extend a sample of a material. The force is then removed, and the variation with the strain of the applied stress is shown on the graph. Which point on the graph could represent the elastic limit for the material? Okay, so let's look at this graph. I stretch, well, remember, stress is related to the force, so I apply a force, and strain is related to the extension. So as I apply the force, I go up, I follow the arrow on this graph. The greater the force, the more the material expands. Its length increases over its original length. And when I'm going from 0 to A and then almost all the way to B, what I find is that, and at A, and certainly at A, what happens is that the stress is directly proportional to the strain. It's a straight line, so it's a direct proportionality between stress and strain. But at B, what do you notice? So at B, I notice that the graph is no longer a straight line, it starts to curve, and stress is not proportional to strain. So B lies just after the limit of proportionality. So the limit of proportionality is the maximum point where stress is proportional to strain. Now what we know is that the elastic limit lies just after the limit of proportionality. Okay, so at B, what we should have is the elastic limit. And that's because at C, we have gone well past the elastic limit. If this was a spring, for example, at point B, you can imagine that trying to get the spring back to its original shape is not going to work. It's going to have some strain even without any stress on it. At C, it's definitely not going to go back to its original shape. If I remove the stress, there's still going to be some strain. So we've well past the elastic limit at C. And so point C will be that point which is the elastic limit. And how do we know this? It's a point that comes shortly after the limit of proportionality is exceeded. I'm going to write that down. Shortly after limit of proportionality has been exceeded. And so this is option B. Option C is well past the elastic limit. We're definitely not going to get the spring back to its original shape at point C. And at D, the object is now undergone plastic deformation. It's not going to go back to its original shape at all. In fact, the stress has been removed and it's still been extended over its previous original length. So that question, the correct answer was option B. The next question is question 641. It comes from the summer 2020 exam, question paper 1, variant 2, and it's question 18 from that paper. So it's another fairly tricky question. It says an elastic cord of unstretched total length 16 centimeters and cross-sectional area 2 times 10 to the minus 6 meters squared is held horizontally by 2 smooth pins at a distance 8 centimeters apart. The cord obeys Hooke's law. A load of mass 0.4 kg is suspended centrally on the cord, and the angle between the two sides of the cord supporting the load is 60 degrees. And we want to find the Young's modulus of the material of the cord. Now, each one of these answers here, unfortunately, is a common error. So above this question just being difficult, it is very easy to make a single error and see your answer appear in the choice of answers. My suggestion is to leave these questions to later if you feel like they are a bit challenging. But again, it all depends on how comfortable you are. Okay, so initially the unstretched cord has a total length of 8 and 8. There's two sides to this cord, so that's 16 centimeters. And finally, I have a 3-sided cord, each side with a length of 8 centimeters, 8, 8, and 8, with an angle of 60 degrees between the left and right hand sides of 8 centimeters, meaning the total length is now 24 centimeters. So clearly there's some extension happening. When there's extension, we can calculate Young's modulus. And the force that's going to provide the stress is the weight of the mass that's being hung on the cord. Now, this entire thing is in equilibrium. So I'm going to initially balance the forces just to see what happens. And at the point where the mass is hanging, I have the weight of the mass acting downward. I'll call it F. Doesn't really matter. I can name it what I want. And then I have a tension in the cord, T, pointing up and to the right. And the same tension, there's only one tension in this cord. It has the same magnitude pointing up and to the left, acting on that point. And the angle between the vertical and each of these tensions is both 30 degrees. So 30 and 30 makes 60 degrees. Okay, so the force here, F, acts vertically downward, and it's equal to the vertical components of each of these tensions. And there's 2 of them. So that's 2t cosine of 30 degrees. And you can do the geometry to see that that's correct. So t cosine 30 degrees is the vertical component of one of these tensions. There's 2 of them, and the mass is in equilibrium. So it must be 2t cosine 30 degrees. This means that the tension T in the cord is F divided by 2 cosine 30 degrees, which I'm then going to write as mg, because the force is simply the weight of the mass, mg over 2 cosine 30 degrees. And look, I mean, it might be good practice for you to just put in your values immediately, since you know the mass, and you know g is 9.81, and you can find this tension numerically, meaning it's a little bit less algebra to do later on. But let's just do the algebra. Okay. And remember, there's only one tension in the cord. So don't forget that this cord only has one tension in it. So everywhere the tension is the same, and this tension causes the string, or the cord rather, to extend, and this extension is the extended length, 24 centimeters, minus the original length, 16 centimeters, which is 8 centimeters, which is 0.08 meters. I'm just going to keep everything in meters so that I can just do my calculation in one step. Now, Young's modulus, which is what we want to calculate, is the force that is extending the chord T times the original length divided by the surface area, the cross-sectional area of the chord, multiplied by the extension of the chord. Remember, this comes from stress over strain. That's where I get that equation from. It's force times original length over cross-sectional area times extension. And then I can replace T with the expression I have above, mg over 2 cosine 30 degrees. So this is mg L naught divided by 2a times extension E times the cosine of 30 degrees. So yeah, it is a bit mathematically heavy, but prevents me from having any rounding errors. Now I can put all my values in because I know all of these values. The mass is 0.4 kgs. The free fall acceleration g is 9.81 meters per square second. The original length of the chord was 0.16 meters, or 16 centimeters, divided by 2 times the cross-sectional area is given, 2 times 10 to the minus 6 square meters, so that's already in the correct units, 2 times 10 to the minus 6. The extension is an extra 8 centimeters, 0.08 meters, times the cosine of 30 degrees. And what do we get? We get a Young modulus for this material of the chord to be 2.3 times 10 to the power 6 pascals. So there were many places where errors could occur. This corresponds with option C, by the way. So the correct answer there is option C. There were many ways that you could have sort of went astray from the correct working for this problem. But, I mean, these are as difficult as they get. So if you understand the logic behind these kinds of problems, then you're gaining a valuable problem-solving skill, which will help you in all of your physics journey, not just in this topic. But this kind of question is common because calculating Young modulus can be complex, so it's easy for examiners to manipulate this concept to make questions relatively difficult. So the next question is 642. It comes from the summer 2020 exam season. It's question paper 1, variant 2, and it's question 19 from that paper. We're told that a student is investigating the mechanical properties of a metal. He applies different loads to a long thin wire up to its breaking point and measures the extension of the wire for each load. He then plots a graph of stress against strain. So stress on the y-axis and strain on the x-axis. Stress being your independent or dependent variable and strain being your independent variable. Now the student repeats the experiment with the wire made from the same metal and with twice the original length and half the diameter. And we want to know which of the following graphs will be obtained. So it's the same metal, meaning it will have the same Young modulus. The length is doubled and the diameter is halved. Now what do we know about Young's modulus? We investigate what Young's modulus is. It's stress over strain. Notice how all the graphs have the same shape but different values, meaning the gradient of the graphs will be different, but everything else will be the same in terms of the relationship. So Young's modulus is stress divided by strain, which means that if I rearrange this equation, stress is equal to Young's modulus E times strain. Now if I'm using two different wires and I'm plotting a graph of stress against strain, I can use two different wires to plot stress against strain, but I'm going to get the same gradient. So irrespective of what I get on the y and the x-axis, I'm going to have the same gradient. So essentially, I'm going to have the same graph because both wires are made from the same material. So since the Young modulus is the same for both wires, at all points the gradient is going to be the same. If the gradient is going to be the same at all points, then I must have that the graph for stress against strain for the second wire is identical to the graph for the stress against strain of the original wire. And that corresponds to option B. So whenever I'm drawing or plotting a graph of stress against strain, as long as I'm using the same material, I have the same Young's modulus, the graph is going to look exactly the same. If I use metals that are different, or rather materials that are different, then my graph of stress against strain will change because the Young modulus for those two materials will differ. And so you don't really have to do any calculation or mathematical manipulation. You could simply just, from your knowledge of the concept, see that your answer would be B in that case. Okay, question 543 is from the summer 2020 exam. It's question paper 1, variant 3, and question 20 from that paper. So another one of those that is quite tricky. Now we are told that the diagram shows a simplified model of a building with 4 identical heavy floors. The spacing of the bottom floor from the ground is twice that of the spacing between the floors. Between each floor, equal numbers of vertical steel supporting rods of negligible mass compared with the floors. The rods are of different diameters so that the stress in each rod is the same. And we want to find the ratio of the diameter of the bottom rods to the diameter of the top rods. Okay, so basically the bottom and top rod, the bottom rods are twice the length of the top rods. So the original length is twice as much for the bottom rods than it is the top rods. And the stress is the same for the bottom and the middle and the top rods. So all of the rods have the same stress. And in order to do that, they change the diameter slightly. So some are wider than the others. So what I want to do is figure out what the force is acting on the bottom rods, and then find out what the force is acting on the top rods, and then work out what their areas, the relative areas are going to be. Because if I know what the areas are going to be, I can find the ratio of the diameters. So the force on the bottom rods, and I'm just going to do one individual bottom rod. So the force on the bottom, rods at the bottom, is equal to, let's say the mass of each of these floors is m. Then there's 4 floors above the bottom rods. So the total force is 4 mg. But I'm going to assume that I have 2 of these rods. So the total force is going to be divided between these 2 rods. So that each rod is going to support half of the weight of the floors above them. So 4 mg over 2 is 2 mg. Now, what about the force that is felt at the top rod? Now, the top rods only have one floor to contend with. So it only has 1 mg, but it's going to share this between 2 rods. So that's mg over 2. And so the force that is shared between the 2 top rods is a half mg. Now, the stress, sigma, is defined as force per unit area, and that's the cross-sectional area of each of these rods, right? Which means that the area, the cross-sectional area, is the force divided by the stress, just rearranging the equations. This means that the area of the bottom rods, the cross-sectional area of the bottom rods divided by the cross-sectional area of the top rods, is going to be, and the stresses are going to be the same as they told us. The stresses are equal, they're the same. So it's the ratio of areas is simply going to be the ratio of forces. So area, cross-sectional area of the bottom, or divided by the cross-section area of the top, is going to be the force felt by the bottom rods divided by the force felt by the top rods. Okay, and we have expressions for this. We know that this is 2 mg divided by a half mg, and so this is 4 mg. Oh, right, sorry, mg's cancel, but the ratio is going to simply be 4. Okay, so that ratio of areas is going to be 4, but we want the ratio of diameters. And so what do we know? We know that area, let's assume these rods are cylindrical. and so they have a circular cross section. So the area is pi r squared, or 1 over 4 pi d squared, meaning the diameter, where d is the diameter is the square root of 4a over pi. You just double check my mathematics there, but this means that now if I want the ratio of diameters, the diameters of the bottom rods to the top rods, which is what the question asks for, then this is the square root of the ratio of areas. The square root of the ratio of the area of the bottom rod divided by the area of the top rod. But hey, wait a minute, I already know that ratio. This is the square root of 4, which I've already calculated, which is 2. So the ratio of diameters of the bottom rods to the top rods is 2, meaning the bottom rods have a diameter that's twice as big as the top rods. So this was another complicated question. But my suggestion would be to find the ratio of the areas first, and then use it to determine the ratio of the diameters. Or you could have just done everything in one go, and instead of simplifying the ratio of areas to 4, you could have just went one step further and found the ratio of diameters. Either way, this was quite a mathematical problem and also quite conceptual at the same time. But another one of these that are quite tricky. And so I get the answer here to be A. The ratio of diameter of bottom rods to diameter of top rods will be 2. So fairly complicated questions. We are encountering a few of these complicated questions, but we will learn from them and they improve our problem solving skills. So we're quite happy to work on these. The next one, luckily, is not as complicated. It comes from the March 2019 exam, question paper 1, variant 2, and it's question 19 from the paper. A metal wire fixed at one end has length L and cross-sectional area A. The wire extends a distance E when mass M is hung from the other end of the wire. What is an expression for the Young modulus E of the metal? Okay, so I have a metal wire that's holding up it's fixed at one end, and it's holding up a mass M at the other end. There's obviously the weight of this mass is causing an extension. The metal had an original length of L, but because it's being extended by the mass that's hung at the end of it, the extension is little e. What we know is that Young's modulus E is stress over strain, which is the applied force divided by the multiplied by the original length L divided by the cross-sectional area of the wire times the extension E. And in this case, the force is the weight of the mass mg times the original length of the wire L divided by the cross-sectional area A times little e, the extension. And we can see that luckily this corresponds to one of the options that are there, and that's option B. So happy to get a question that is a little bit better than the ones we've been seeing thus far. So that's mgl over AE, the Young modulus. The next question is from the March 2019 exam, from question paper 1, variant 2, and it's question 20 from that paper, and it's about springs. Now we're told that a spring has a spring constant of 6 newtons per centimeter. It is joined to another spring whose spring constant is 4 newtons per centimeter, and a load of 80 newtons is suspended from this composite spring. We want to know the extension of this composite spring. Now, it is important to remember that if a load is hung at the bottom of 2 springs that are in series, then that load is applied to both the springs. It doesn't get split between the springs. It is 80 newtons on the bottom spring and 80 newtons on the top spring. So let's work on the upper spring first and then move to the lower spring. For the upper spring, the force, which is simply F because the same force is applied to both springs, is equal to its spring constant or force constant K1 times its extension E1, which means its extension E1 is going to be the force divided by K1. If you know the equation for springs in series, by all means use them, but I'm doing it via the first principles of what happens when springs are in series. For the lower spring, the same force is applied, but it has a different force constant K2 and a different extension E2, which means its extension E2 is the force applied divided by its force constant K2. And so the total extension is what I want. I'll call it, is simply E1 plus E2, which is F over K1 plus F over K2. And this is AT, and I want the extension in centimeters, so I can leave my force constant in newtons per centimeter. That's AT over 6 newtons per centimeter plus the same force AT divided by 4 newtons per centimeter, which gives me an extension, total extension of 33 centimeters. And this corresponds with option D. So you can remember the equation for springs in series and springs in parallel, or you can derive them if you are uncertain about how to remember what the total spring constant would be, or the effective spring constant would be. But essentially the total extension of the spring will be 33 centimeters. So the load is going to be applied to both of the springs equally. The next question is 646. It comes from the summer 2019 exam, question paper 1, variant 1, and it's question 20 from the paper. We're told that a spring of original length 100 millimeters is compressed by a force. The graph shows the variation of the compressing force with the length of the spring. And we want to know what the stored energy in the spring is when the length is 70 millimeters. Okay, so this problem gives me a spring when the spring is 100 millimeters in length, that is 0.1 meters, there's no force being applied, that's the original length. But as I apply a greater force, as I move left on this graph, then the spring gets compressed. It becomes smaller, that's why the length is getting smaller. Now to find the energy stored in the spring, I could use the area under the graph. If you're comfortable with that, that's great. But what I'm going to do is find the spring constant first, and then use the spring constant to calculate the stored potential energy in the spring. What I know is that the force is the force constant K times the extension delta L. Meaning that if I draw a graph of force against length, that the force constant is going to be the gradient of the graph. Always is the gradient of the graph. And I'm going to find the gradient, and I'm going to find it in newtons per millimeter, then convert it to newtons per meter. So the gradient of the graph, I'm going to say, is 12 divided by 100 minus 40, which is 0.2 newtons per millimeter. It's a per millimeter here, so it's going to be the other way around. I get 0.2 newtons, actually rather 0.2 times 10 to the power 3 newtons per meter. 10 to the power 3 newtons per meter. So that'll just make my final answer will come through in SI units automatically. Now the elastic potential energy stored in a spring, remember, is a half K times, in this case, compression squared, delta L squared. And that's a half. Now we've already calculated the spring constant, 0.2 times 10 to the power 3 newtons per meter, multiplied. Now the compression of the spring when its length is 70 millimeters is 30 millimeters, because the unstretched length is 100 minus 70. And so what is the compression? It's 30 millimeters, so we have to multiply that by 10 to the minus 3 to get meters. And we square this value, and we get the elastic potential energy stored in the spring to be 0.09 joules. and this corresponds to option A. I always get confused when I have to find the area under the graph to try and calculate elastic potential energy. So what I do is I use the gradient of the graph to find the spring constant or the force constant, and then I use the force constant, a half kx squared, to find the elastic potential energy. Again, it's completely up to you, but the method should be one that you're comfortable with. And so that's option A, 0.09 joules. The last question for this video is 647. Comes from the summer 2019 exam. It's question paper 1, variant 1, and question 21 from the paper. We're told that a 0.8 meter length of steel wire and a 1.4 meter length of brass wire are joined together. The combined wires are suspended from a fixed support and a force of 40 newtons is applied as shown. The Young modulus of steel is 2 times 10 to the 11 pascals, and the Young modulus of brass is 1 times 10 to the 11 pascals. Each wire has a cross-sectional area of 2.4 times 10 to the minus 6 square meters. They both obey Hooke's law, and we want to calculate the total extension, ignoring the weights of the wires. Okay, so I know that there's 2 wires that are going to undergo different extensions because they're made from different materials, but they both have the same force acting on them. Now we know that Young modulus, it's always good to write the equation out for Young modulus because immediately as you see the equation, you see the letters and symbols on paper, your brain can start to piece things together, to see what information you have and what information you need. So Young modulus is stress over strain, which is force times original length over cross-sectional area times extension, which means that the extension is the force being applied times the original length of the wires divided by the cross-sectional area times the extension. Now each wire has the same cross-sectional area, which makes our life a little easier. And the total extension is going to be the extension of the brass wire plus the extension of the steel wire. And that's going to be F L naught over A. Oh, actually, I have made a mistake in this equation, so I rearranged this equation to solve for the extension. So this E in the denominator is big E. It's the Young modulus. So little e is FL naught over A times big E. So this is FL naught over A times big E for steel plus FL naught over A times the Young modulus for brass. And now it's simply a matter of putting in all the numbers, which will be a little bit messy, but rather be messy but not difficult to solve. So the force is 40 newtons applied to each of these wires. They are in series. It's 40 times the original length of the steel wire was 0.8 meters divided by the cross-sectional area, which is given 2.4 times 10 to the power minus 6 square meters, so the units are fine, times the Young modulus for steel was given as 2 times 10 to the power 11 pascals. And then we add that to the identical values for brass. The same force, 40 newtons, times the length of the brass wire, which is 1.4 meters, divided by the cross-sectional area, 2.4 times 10 to the minus 6 square meters. And the Young modulus for brass is given as 1 times 10 to the power 11 pascals. And if we add these two values together, we get the total extension of the composite wire to be 3 times 10 to the minus 4 meters. And this corresponds to option B. So the total extension is 3 times 10 to the minus 4 meters. So in a question like this, similar to the way we did the springs, the only difference is here when we have wires, we usually talk about different materials, which means we need to bring an extra element of complexity, that being Young's modulus. And that adds things like force, cross-section area, extension, and so on. But again, the idea is the same. So it is imperative that you get a good grasp of the Young modulus and how wires especially deform when we apply forces on them by a mass, by hanging a mass on them, or some weight or some tension, and so on. And also don't forget your vectors, like we've seen in some of the questions prior to this. This is the last question we'll do for today's video, but I hope this video was helpful. I hope you see the importance of understanding things like Young modulus and strain energy. If you found this video useful, please leave a like, leave a comment down below, subscribe to the channel if you haven't already. From me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.